All right, let's jump right into this. Welcome to the Explainer. Today, we're taking a seriously fascinating journey through the physical dimensions that literally make up our reality. We are going to bridge that gap between measuring simple straight lines to calculating the massive areas and volumes that build the world around us. Now, I know that might sound a bit complex at first, but stick with me. By the end of our time together, you'll see just how beautifully logical the mathematical system of mensuration really is. It's kind of like a giant puzzle, and we're about to put the pieces together. But to truly appreciate how we measure the universe, we've got to step back in time for just a second. Meet Isaac Newton. You probably know him as the father of calculus. It was Newton who completely revolutionized how we calculate physical space. He used calculus to solve these incredibly complex problems, like finding the exact areas of completely irregular shapes and the precise lengths of curves. These were concepts that fundamentally changed our grasp on the universe itself, a real game changer. So here is our roadmap for today. We'll hit point 1, the father of calculus, point 2, decoding metric language, point 3, converting mass and capacity, point 4, the area conversion trap, and finally point 5, visualizing 3D volume. Let's get right to it.
Starting off with section 1, the father of calculus.
So, born in Lincolnshire way back in 1642, Newton wasn't just some guy sitting around thinking about theories. He was actually highly practical. I mean, the guy designed the first reflecting telescope. But his absolute crowning achievement? That happened in 1687, when he published Principia Mathematica. Before that book dropped, humanity knew the planets moved, sure, but they didn't really know why. Newton gave us the laws of motion and universal gravitation. And mathematically speaking, his discovery that integration and differentiation are inverse operations, that is literally the bedrock that lets us confidently calculate the natural world today. Absolutely crucial. Moving right along to section 2, decoding metric language. Now here's a really cool secret about the metric system. You actually don't need to memorize a bunch of arbitrary unit sizes if you just look at the language itself. The prefixes literally hand you the math. Centi comes straight from the Latin word centum, meaning 100. So it makes perfect sense that a centimeter is exactly 1/100th of a meter. Milli comes from the Latin mille, meaning 1,000, making a millimeter 1,000th of a meter. And kilo? That's from the Greek kiloi, which also means 1,000, telling us immediately that a kilometer is 1,000 meters. It's not just a naming convention, you guys. It's a built-in set of mathematical instructions. Take a look at this table. Notice how it maps out these simple, everyday measurements. 1 kilometer equals 1,000 meters. 1 meter gives you 100 centimeters. 1 centimeter holds 10 millimeters. It's elegant, it's simple, and it's all based on these clean base 10 shifts. You literally just move the decimal point. But definitely keep this simple 1D math in the back of your head, because as we're going to see in just a minute, things change drastically when we start adding dimensions. All right, let's step into section 3, converting mass and capacity. We're shifting focus now from just drawing basic straight lines to actually measuring the weight and the liquid volumes we interact with every single day. And the crucial point here is understanding the difference between capacity and volume. They are closely related, sure, but they are slightly different things. Capacity is all about the void. It refers strictly to the space inside a container, like how much liquid can it physically hold. Volume, on the other hand, refers to the sheer amount of physical space that the container itself occupies in the world. Make sense? Let's see how these concepts build into an incredibly beautiful relationship. Think about a cube. Let's say it's exactly 10 centimeters long, 10 centimeters wide, and 10 centimeters high. The capacity of that specific cube is exactly 1 liter. Now, if you fill that 1 liter perfectly with water, it has a mass of exactly 1 kilogram. And if you break that single liter down into 1,000 milliliters, each one of those single milliliters takes up exactly 1 cubic centimeter of volume. It is a perfect 1-to-1-to-1 bridge between physical length, liquid capacity, and physical mass. How cool is that? But okay, now we have to talk about a danger zone. Welcome to section 4, the area conversion trap. This is literally the most common pitfall people face when shifting their thinking from a one-dimensional line to a two-dimensional plane. I want to pose this question directly to you because it really challenges our basic intuition. If you know for a fact that 1 straight meter equals 100 centimeters, then logically a square meter should just be 100 square centimeters, right? I mean, it sounds completely correct based on the base 10 rules we literally just learned. Well, actually, let's walk through the actual logic step by step. Picture a square drawn on the ground. The length is 1 meter and the width is 1 meter. The area is 1 times 1, which is 1 square meter. Simple enough. Now let's swap those side lengths into centimeters. The length is now 100 centimeters, the width is 100 centimeters. To find the area of this square in centimeters, we have to multiply the new length by the new width. We have to multiply 100 by 100.
And boom, that gives us 10,000 square centimeters. Let that sink in. A single square meter doesn't hold 100 square centimeters, it holds 10,000. And why? Because you aren't just scaling a straight line anymore, you are scaling an entire plane. You have to account for both dimensions simultaneously. This is exactly why you cannot simply move the decimal point once when you're dealing with area. It's a massive trap.
Which brings us to our final and most extreme dimension, Section 5, Visualizing 3D Volume. So if area scales that much faster than length, just imagine what happens when we add depth to the mix. When we talk about volume, we are talking about massive, real-world physical structures. Just look at the pyramids of Giza. Mensuration is the branch of mathematics that actually allows us to measure monolithic 3D objects exactly like these. And to do that accurately, we really have to understand how dramatically volume multipliers scale. Let's apply the exact same logic from our area trap, but this time, let's push it to a 3D volume calculation. Imagine a perfect cube. It is 1 meter long, 1 meter wide, and 1 meter high. Its volume is exactly 1 cubic meter. Now let's convert those three sides to centimeters. That is 100 centimeters long, 100 centimeters wide, and 100 centimeters high. To find the total volume, we multiply all three of those dimensions together. 100 times 100 times 100.
Any guesses? The result is a staggering 1 million cubic centimeters. No way, right? But it's true. One single cubic meter occupies the exact same amount of physical space as 1 million cubic centimeters. It's just an incredibly powerful reminder of how adding a third dimension radically multiplies the effect of our measurements. And honestly, this brings us right back full circle to Isaac Newton and his Principia Mathematica. To truly understand the mechanics of the universe, we absolutely must be able to precisely measure and map its space. Whether it's that perfect 1:1:1 ratio of a liter of water, the 10,000 square centimeters hiding inside a single floor tile, or the 1 million cubic centimeters packed into a moving box, the math provides the foundational rules of reality.
So, I want to leave you with this thought to carry into your day. Next time you look at a room, a container, or even just a building, ask yourself, are you intuitively calculating that physical space in simple lines, in expanding squares, or in millions of invisible cubes? It really entirely changes how you perceive the world around you, doesn't it? Thanks so much for joining me on this explainer, and keep exploring those dimensions.